Okay, in this video we'll talk some more about sequential design or finite state machines, and specifically we'll get into the design of sequential circuits. First, a quick review. So we saw last time how we could go from a sequential circuit and then read off the Boolean expressions for both the outputs as well as the flip-flop inputs. Also, sometimes this is called the flip-flop excitation functions. And then from our Boolean expressions, we can then fill out a next state table and then write out the state diagram. And from the state diagram, we can infer what the circuit is actually doing or write a verbal description for it. So what we were really doing was a sequential circuit analysis. But we can also go the other way and start off with the verbal description of what we'd like to build for our sequential circuit, and then create a state diagram, a next state table, a Boolean expression, and then finally the sequential circuit. And so this is what we would call sequential design. Another name for sequential circuit is something called a state machine, or more specifically, a finite state machine, or FSM for short. So our sequential circuit or finite state machine has some combinational logic, some storage elements, and so my combinational logic takes as input the external input X as well as the current state of my sequential circuit, the outputs of my flip-flops, and then generates the inputs to the flip-flops, which will determine the next state, as well as the outputs. So for a finite state machine or a sequential circuit, when can the state change? So while the input could change, X can change at any time, and the same thing for the flip-flop inputs that come out of this combinational circuit, the flip-flops themselves, or the state of the circuit, is only going to change on the clock pulse. So the state only changes on the clock pulse. Now how about the outputs? When can they change? Well, for this, it depends on the type of finite state machine that I've designed, and there's two classes of finite state machines which are very similar and differ only in how their outputs are created. So there are two types of finite state machines, Mealy and Moore finite state machines. And as you can see, they're very similar. The only difference is in how the output is created. In the Mealy state machine on the left, the output Z is a function of both the input X as well as the current state. But in the case of a Moore style output, with a finite state machine, the output is only dependent on the current state. Now here, there might be some combinational circuit that takes the outputs of the flip-flops, but in many cases it's just directly taken from the flip-flop outputs. So another important question is how many states are there, or how many states are needed for a particular sequential problem. So with one flip-flop, I have one state variable, which can take on one of two states, 0 or a 1. With two flip-flops, I have two state variables, and so I have four states, 0, 0, 0, 1, 1, 0, 1, 1. And with three flip-flops, obviously then I have 8 states, 0 up to 7. Okay, so let's look at an example of designing a finite state machine, or a sequential circuit that solves a particular problem. So let's say I wanted to design a circuit that controlled a vending machine that dispensed some type of candy. And that candy cost 15 cents. But my vending machine could only take 1 nickel or 5 cents at a time. So the first thing that I'm going to want to do in general for any sequential design problem is think about what are the states that are needed and then write down those states before I jump right into the state diagram. So for example, I'm going to have one state where I start off where I have no money. I'll then have a state where I put in 1 nickel, 5 cents, 10 cents, and then 15 cents. And so my vending FSM is going to have one input, we'll call this N for nickel, and then one output C for controlling when my candy is dispensed or not. So let's draw our first state, the no money state. And in the no money state, when I'm just starting off, I shouldn't dispense the candy yet because no money has been put in. And I'm going to go ahead and stay in this state perpetually as long as no money is put in. As long as I don't have any nickels, so nickel is 0, then I'll stay in this same state. If a nickel is put into the machine, then I'm going to go on to the next state, which is the 5 cent state. Again, I'm not going to dispense any candy because I've only put in 1 nickel. Now in this state, again, I'll also stay here as long as I haven't put in any more nickels. But if I put in another nickel, then I'll move on to the 10 cent state. And if I put in one more nickel, now I've put in enough money, and so now I'll get my candy. Now, from this state, If I don't put in any more money, then on the next clock pulse, I'm going to go back to the first state where I have no money in the machine yet. But if I put in another nickel right away, then I'm going to go ahead and go back to the 5-cent state. And so that's my FSM for the candy vending machine. And this particular FSM, I built this with a single Moore style output. Now note that because the output only depends on the state, which is the case for the Moore FSM output, we can go ahead and write the output inside the circle itself. This is as opposed to a Mealy finite state machine output, which we list on the edges, because it depends both on the current state, the circle that I'm in, as well as the input, which is listed on the edge of this graph.